In this panel we have a GeoGebra worksheet which has several features of the GeoGebra for integration, slope fields, and initial value problems illustrated that are built in to the GeoGebra scheme. First, observe we have the function x squared plus 2, and we have a slope field for that function. So this slope field shows a collection of direction lines that are created based on the x value by squaring the x value and then adding 2. So the slopes here are pretty steep. We also see a solution to the differential equation with the initial value given passing through the point -1, 0. And also we have here the length of the segment from the value 0 to the value at 2, showing us the solution to this differential equation with the initial condition that the value at -1 is 0. And we see that when the value input is 2, the value for this differential equation solution will be 9. We also see on the graphical side here, in this frame, we see the graph of x squared plus 2, and we see the integral of the function visualized from -1 to 2 as the region between the curve and the x-axis, x equals -1 and x equals 2, and that integral is treated as the area of that region. So it is the number 9. So we have two interpretations here. The initial value problem, the net change is 9 in the slope field, and the area of this region is 9 for the graphical interpretation in the Cartesian graph. These are all visualized here by having the buttons for these expressions turned on. So I'm going to turn off the definite integral here is 9, and now I'm going to show you the left-hand sum. That's left sum of the function a, b, n. That's the parameters that you use as the code for this function f. A is going to be -1, b is 2, and we find the value of this number is 8 16/100. That's the left sum. The lower sum, given here, is the sum that comes by using the smallest value of the function on the interval as the height for these rectangles. Again, we have 4 rectangles, and the function is still x squared plus 2. And we're using the smallest value of the function on that interval for the height of the rectangle. That's the lower sum. We have a numerical integral. This is finding the integral numerically, and it doesn't tell us how precise this estimate is, but because this is a rather simple function, the estimate is exactly the same as the definite integral here. So we see they're exactly the same. That's the integral, and here's the numerical integral. We also have built in a rectangular sum with a proportion telling us where in the interval we would choose the point. Here I'm using 1/2, so each interval I'm using the midpoint of that interval to determine the height of the function. So this is the midpoint estimator because I'm using 1/2 for my rectangular sum. It's still this function's f. We're going from a to b. We have the same number 4, but now we're using 1/2 as the proportion on the interval that we will use for the estimator for the choice of the value. That's the rectangular sum. We also have built in a trapezoidal sum determined by n, and we have an upper sum using the maximum value. of the function on the interval for the determination of the. And that's the built-in tools that GeoGebra gives you for visualizing a differential equation and its solution. Here I'm going to turn off the solution here. This is the code is solve ODE, the name of the function and the initial value or the point that you want to be on the curve. And I'll turn that off. And the slope field is given by the coding slope field, the name of the function, and the number. I'm using the number squared, so n is 4, so I'm using 16 as the number that determines the size of these and number of line segments drawn in the slope field. So there's our initial value, solution in the slope field. This line here is actually something that I drew using the solution to give the net change in the value of the function from when it's 0 at -1 to the value that the solution curve gives you when the x is 2. And that length of that segment is 9, corresponding to the integral of the function represented on the graph as the area of the region enclosed by the graph of the function, the lines x equals -1, x equals 2, and the x-axis. We can see with this example how the number n affects this. We'll look just at the upper sum here and change that number to 8, and that gives us a more precise estimate here of the definite integral with the upper sum. And there's 11, and if I'm going to take off the upper sum and put on the rectangular sum here, that's the midpoint, and that gives you an estimate of 8.98 compared to the trapezoid estimate, which is 9.04. So those are two different estimates, both closer than any of the single point estimates at endpoints or max or mins. And we can raise that n up to a pretty high level on this example. This n is 20, and we're within, with the trapezoid, within 100th, and for the midpoint we're also within 100th of the exact answer, which is 9.